these three chapters. Remember that it is covered in your methods of assessment. Let me briefly explain to you. This is course learning outcome number 2. All right. Previously, we cover course learning outcome number 1. All right. Today, we are going to cover course learning outcome number 2, which is the student should be able to calculate, analyze fluid dynamic problem using Bernoulli equation, concepts of control volume, conservation of mass, and energy equation. All right. So when you take a look about this chapter, so you are going to learn the Bernoulli equation. That is part of your CLO number 2, which is course learning outcome number 2, to be able to calculate and analyze the Bernoulli equation related problem. All right. So far you understand, yeah? So next, we should proceed on this lecture. All right. So I think, I think before we start our class, let we start with Ummu Kitab Al-Fatihah first. Bismillah. Okay, now we're going to go deep in chapter 3, which is the introduction to fluid in motion. Previous chapter, we have learned the fluid static or fluid at rest, where the fluid we assume it is no motion at all. However, in this chapter, we're going to explore on the fluid in motion. So definitely when you see around you, the fluid is always in motion when there is a disturbance, all right? So here, the introduction 3.1, the general equation of motion in fluid flow are very difficult to solve, right? It means it is very complex to solve when you have the fluid flow, because this requires simplification assumption. Secondly, in some cases, viscosity can affect flow significantly, whereas in other, it can be neglected. All right. So in this case, we're going to do some assumption to simplify the process. All right. Secondly, we're going to omit the viscosity effect. This is where we simplify the process. This is our assumption. So, as we mentioned earlier, you can see description of fluid motion. All right. So, what is the description of fluid motion? When we involve of the motion of the fluid, for example, the fluid consists of the particle, right? So, the particle, how we describe the motion of these fluids? So, we have two types of description. This we call as a Lagrangian. This is the person discover Lagrangian and Eulerian description of motion. So when people ask you what type of fluid motions description, there are two, which are Lagrangian and Eulerian description motion. So when describing the flow field, think of the individual particle. So here, what is the Lagrangian description? All right, we start with the Lagrangian description. It is on the fluid particle basis, where the description of fluid motion, for example, the position, velocity, and acceleration, where individual particles are observed. Alright, so this is where the individual particles are observed one by one. That is why we consider as fluid particle. We observe one by one the particle. For example, we have 5 particles. That means we observe 5 particles at that time as a function of time. So, however, when we talk about Eulerian description, it is on the opposite side. It is not considered at all about the fluid particle. However, it considers more on the flow field. So, what it means by the flow field is the description of fluid motion where the flow property are function of both space and time. Alright? So I believe in your secondary school, you learn physics, right? So in the physics, you study the motions of the car. For example, you remember your tape. There is the tape and then there is the motion of the car. So that motion you consider as a Lagrangian description. Previously, we already learned, but we never know what type of description. In your secondary school, you learn physics. That is the Lagrangian description. But in today's technology or today's engineering world, we are going to learn about Eulerian description. So now you're going to shift from your secondary to university level, where you're going to learn from the Lagrangian you have learned, and then you're going to convert to Eulerian description. So in Eulerian description is very important in today derivations. So this consider the flow field. Alright, so this is example. You can see this is Eulerian, the new methods. Alright, this is fixed point. Alright, so we consider the space. This is the space x, y, z and time. However, for the Lagrangian, we consider more on the time only, the particle time only. So this is where the particle, we measure particle, the flow particle one by one. However, this is the field. Alright, so I think let me draw so that you will be more clear on this. Okay. Alright. So let's take a look about this. Okay. Okay, for example, this is Eulerian, alright? This is a new method that we're going to learn. This is the old method where you learn in your secondary school. This refers to only time. However, Eulerian considers space and time at the same time. So for example, the Eulerian more on the flow field. So this is the field. Alright? It's like a region. Can we consider the flow? The field is like a region, the space. Alright? So this is the particle. Alright? And then particle entering this region. So we are actually measuring this space only. Alright? We actually measuring the velocity of this space only. However, for Lagrangian, we are measuring, this is particle. We are measuring this individual particle. The particle flow. Every detail of the particle we measure. So we have 6 particles of fluid motion. So we measure this velocity. Velocity 1, velocity 2. However, this is where we measure only the region only. That is why we consider the space X, Y, and Z. This is X, Y, and Z space. This is measured in terms of time only. At time equal to 2, what happened? The particle will flow. So that is actually the big difference between the Eulerian and Lagrangian flow description of motion. So I hope you understand, yeah? So far, do you guys clear on this? Everyone? Are you okay? What's the difference between Eulerian and Lagrangian? Alright. So Lagrangian more on fluid particle. Remember, it is space. It is involved of this one. Alright. The fluid particle. And however, for the Eulerian, it is involved of the flow field. Alright. So next, after we have learned the flow description, whether it is Lagrangian or Eulerian, alright. So we need to know the steady, whether the flow is steady or unsteady flow. So for example, this is the this is the highway, or we call it as this is the water flow. Alright. So the steady flow means the flow quantity do not depends on time. So it is independent, we call. It is not rely on time. So when you see this is steady, this is now. This is future. It is steady. It is the same. For example, velocity, you can see here. Alright. Velocity 1 here is equal to velocity 2, whatever it is now or future. For the case of unsteady, this is velocity 1 and this is future. The next time, the velocity 2 is different from velocity 1. This is we call unsteady. It is related directly with time. With different time, will have different velocity. This is whatever time it is, whatever it is past, now or future, it is the same. That is why we call it as a steady flow. So that means all the property, the velocity property you can see here, and pressure property and density of property over time is 0. That means constant. It doesn't change at all. So that's we call as a steady flow. And then after you have learned steady and unsteady flow, and then in the flow itself, there are 3 kind of flow. We call as the path line, the straight line, and the streamline. So what are those of this line? So remember, the line is come from the fluid particle. The path line, on the other hand, is the locus of point. Remember what is locus? Locus is the moving point. Alright? So in other words, we can say that locus is the moving point. Locus is a moving. Something is moving. We call as a locus. Moving point transverse. This is from one point to another by a given particle as it travel in the field. Right? So for example, this is your particle. And then this particle flow. So you can see one particle, locus of this particle moving. This is time 1 and this is time 2. It is moving. So we call as the path line. And secondly, the straight line we call as the instantaneous line, whose points are occupied by all particles from the specified point. For example, this is the fluid particle, and this is second fluid particle, this is second, this is third, this is the next. So this is where we call as the straight line. We measure the individual particle, right? However, for the streamline, is a useful indicator of the instantaneous direction of the fluid motion through the flow. For example, we have the fluid flow like this, right? So at the instance of time, for example, at time equal to 3, so this point at time equal to 3, the motion is tangent to the, alright, it is like this, tangential to the flow. So when at time of 4, this instantaneous time is like this. And this one would be like this. So this is the instantaneous direction of fluid motion. We call as the streamline. So next, what are the importance of this line that we have learned? So far, the path line, the straight line, and the streamline is used by the scientists to measure the fluid flow. For example, you can see this is the path line underneath the wave in the tanks of water. This is using the PIV. We call a particle imaginary velocity. So when you go to your labs, you will discover there is the PIV, particle imaginary velocity, that are using the technique of path line. So what you have learned here, the path line is actually will help you in your experiment to discover the fluid motion using the experimental technique. So here, the second one is the straight line in the unsteady flow around the cylinder. So this is where they are using the experimental method. You can see they measure the fluid motions in the straight line. Alright, so this is where I previously mentioned to you what is the streamline, which is the instantaneous flow direction of the fluid motion. For example, this is the fluid start from here, motion from here, and next go to here. So at the instantaneous direction, it is always tangential to the curvature. All right, so it will be like this. So this is we call as the streamline. So in the streamline, we have the formula, which is the velocity. All right, this is the velocity multiply, or we call as the cross product of dr equal to 0. All right, why this is equal to 0? Let's take a look about this. Okay. So, for example, I try to zoom in this one. For example, okay. For example, this is the flow. And then we take the instantaneous direction like this. So definitely, the velocity will be like this. Right? Okay. Okay, sorry. Maybe the velocity will be tangential. Okay, this is the velocity vector direction. So this is V. You can see the direction of V in this direction. So dr, however, where's the dr? So this is dr, the small here. Okay. This is actually dr, the change in radius. So this is our frame, reference frame. So from here, this is our radius, and this is the change in dr from here to here. This is dr, and this is velocity. You can see the velocity motion and the change in r radius is in the same direction. So when those vector in the same direction, we apply the cross product, it will be 0. All right. So I believe you have learned in your basic calculus where the product of same direction for the cross product, it will be 0. All right. So next is where you learn the stream tube. This is another kind of line. Previously, we learned about the path line, the streamline, and the straight line. Now we go on the stream tube. So what is this? What is the stream tube? A tube whose walls are streamlined. So this is, for example, we take the fluid region from C1 and go to C2. So from here, the fluid motion, all right, let me draw. The fluid motion from here, this is, for example, the fluid 1, will transverse and go to here. This is their streamline. This is fluid 2, will go to here. The connecting between the earliest to the next point forming this tube we call as the stream tube. So this is actually the streamline. This is the streamline, the blue color here. All right. Connecting this, making the stream tube. So in a steady flow, all right, remember the steady flow is, it is unchanged of property and it will not dependence on the time. So in a steady flow, path line, straight line, and streamline are all coincident. So that means all is in the same direction. So that is only valid for the steady flow only. If you talk about unsteady, it will be different cases. So after we have learned about this kind of velocity, next we learn about the acceleration. Remember, the acceleration is derivative of velocity. You try to differentiate the velocity with respect to time, it will get the acceleration, right? So here, V, remember we have learned previously, velocity vector, this is velocity vector, okay? All right. All right, so we have learned that in the velocity vector, we have I, J, and K component. This is I in the X direction, J in the Y direction, K in the Z direction. All right, so from here, U is referred to velocity in X direction. V is velocity in Y direction and W is velocity in Z direction. So we combine together, we come velocity vector is equal to Ui plus Vj plus Wk. Alright, this is, remember when we talk about the vector, we have the magnitude and the direction. So how it represent? It will represent like, remember we have velocity vector, we have, this is the magnitude, and this I, J, and k is the direction. So velocity vector is considering the magnitude and direction. Whereas the magnitude, when someone asks you, where's the magnitude? U, V, and W. Direction is I, J, and K. So now you understand, yeah? Okay, next is from the velocity vector, how we comes to the acceleration. How to relate velocity vector to the acceleration. Remember, acceleration is the derivative of velocity with respect to time. So that means we differentiate velocity with time. So velocity over time is acceleration. Using a chain rule from your calculus basic does give the acceleration. So this acceleration is delta V. Alright. This is we call a partial derivative. So what is actually partial derivative? This partial derivative, what is the difference between partial derivative and total derivative? This is D. Total derivative and partial. So actually the difference is the partial focus on the individual component. The total focus on the whole component. Alright. So you can see here. Alright. This is focus on individual component. This is focus on the whole component. So using the chain rule formula, partial derivative V over partial derivative X, dx over dt, you try to use a chain rule by additional of this term, the second term of x over t, y over t, z over t, and remember when we talk about the Eulerian description, we have the function of space and time. The space is x, y, z. The time is the time domain here. So you can see partial derivative of x over dx, you can actually cancel using the chain rule. You will definitely get the dv over dt. So you try to have additional term using the chain rule. Alright, this is the additional term, dx over dt, dy over dt, dz over dt, and one more, the function of time. Since we know that dx over dt is velocity in x direction, y over t is velocity in y direction, and z over t is in the z direction. So remember, u is dx over dt, v is dy over dt, and w is dz over dt. This is the direction, the velocity component in x, y, and z direction. Since we know that this kind of equation related, we can simplify the equation. From here, we try to replace dx over dt with u, dy over dt with v, and w with this kind of term. And here is the simplification process. The acceleration is simplified as u. Remember previously, we replace dx over dt with u. So this is u, partial derivative of v over partial derivative of x. This is fixed, this is keep. We have to maintain this term. This term is maintained, alright, until it becomes this equation. So basically, this is the equations of acceleration. We have simplified further. Alright, so when we talk about the scalar component of the above equation in the rectangular coordinate. So rectangular coordinate consists of x, y, and z direction. So from here, we try to expand in terms of x, y, and z component. Here they are, alright. This is the function of time, you can see. And here is the function of space. Remember, we use the Eulerian description, the function of space and time. This is time. When consider of x, this is u. When consider of y, this is v. Consider of z, this is w. And follow the next part. This is u, VVV and WWW, right? This is UVW. The same thing happened here. So I hope that you can remember this kind of formula when you encounter any related question pertaining to this acceleration. Alright, so after we know that the acceleration is derivative of velocity with respect to time, and this is the solution, this is the equation. And then the acceleration can be further simplified. Now we try to simplify further. Right? As follow. Acceleration is equal to d, we call it total as well as the total. D is a total derivative or substantial derivative, or another field we call material derivative. dv over dt, capital dv over dt. Whatever it is, you have to understand the basic. Acceleration as usual, velocity over time. Alright, the change of velocity, d mean the total change of velocity over total change of time. So derivative here, the d, capital D, means the substantial derivative. So from here, this is as the standard notation we have learned previously. U, V, W, this is the function of space and this is the function of time. Remember, this is the partial derivative. We focus on individual component, right? So when it is involved a velocity acceleration in x, this is u. When in y direction, this is v. When in this z direction, this is w, right? So, however, this frame motion with respect to our observer. So we are the observer, right? We observe the fluid motion. However, if the observer reference frame is accelerating, for example, we are moving and then we look at something, the particle is in motion. So that means we have two frames in motion at the same time. The particle move and we as the observer move. So what happened is we need to consider another factor, which is previously we have learned acceleration equal to A, right? This is the A. This is where the frame motion or the observer is not moving. What happened is the observer is moving or accelerating. So these four components we have to consider. This is where the acceleration, the total acceleration is equal to acceleration we have learned previously, that considered as the space and time, plus the acceleration of reference frame. This is our reference frame. We try to do the second derivative of length. We got the acceleration of the reference frame plus the Coriolis acceleration. This is acceleration due to the Earth's of motion. For example, the motion of Earth is rotating, so we have to consider the motion of Earth. This is the normal acceleration, we call as the angular velocity. This is omega as the angular velocity, and this is the angular acceleration. Alright, so from here, once you learn that if the reference frame is accelerating, then you need to understand the angular velocity and acceleration. So next we go on the angular velocity and vorticity. Since the observer is accelerating, then you need to know this acceleration, angular acceleration, omega. So what is omega? Right? So this omega, angular velocity, and it's directly related to vorticity. So here, this is the region. All right, this is the two plane, x and y plane. So this is a region. We consider the space is dx. All right, The distance is dx, and here distance of y. So this is fluid from point A to point B. This is fluid from point C to point D. You can see the motion A to B involved in the x direction. So it is U. When the direction involved in the y direction, C to D, it is V. Alright? So from here, the velocity from A, alright, this is where they have calculated velocity at A, V minus partial derivative, the half. Actually, this is, we consider the velocity at the center. When going here, it is minus, negative. When it is going to the right, it is positive. When it is going to the top, we have to plus. And the velocity going to the bottom, we have minus. You can see dy over 2 because this is half of dy. Remember, this is half of dy. As the fluid particle move, it may rotate or deform. Alright. Previously, you have learned that when the fluid move, for example, this is fluid particle move. Right? This is particle, the fluid particle move, for example. Okay. Okay, this is the motion of fluid. Okay, this is the motion of fluid. Remember, when the fluid is in this direction of motion. Okay, for example, we consider this is the fluid motion. Okay, so when the fluid motion, normally we consider the motion is like this. Okay, remember this is the fluid motion. However, in certain cases, actually it might not be like this at all. The fluid motion in this case might be, for example, this is motion. Alright, the fluid motion is rotating like this. Sometimes this is like this. In this direction, the eyes will be like this. And in this direction, the eyes will be like this. So now you understand, yeah, the difference between the unchange of motion, unchange of angular velocity, or with the change in the angular velocity. So once you consider that there is a motion, sometimes there would be like no rotation. So this happens when there is the rotation of fluid property. So in this case, as the fluid particle move, it may rotate or deform. So next we will discover what is rotate and what is deform. Alright, the deform means it change the shapes. In a certain flow or region, the fluid particle, this is considered the fluid particle, do not rotate. Sometimes it will not rotate. It is easy. Sometimes it rotates. If the fluid particle not rotate like this, we consider the flow is irrotational flow. So it will not rotate. For example, this normally happen in the flow outside the thin boundary layer on airfoil, the flow around submerged object. So I will show you later on the example of irrotational flow when the flow outside the thin boundary layer. Alright? So this is the angular velocity. We learn about the symbol is omega like this. Angular velocity is the average velocity of two perpendicular line segment of the fluid particle. So this is the basic definition of angular velocity. The average, remember when we talk about average, it is 1 plus 1 over 2. So you know, yeah, what is the average? You plus everything and you divide with the total quantity. So that is the average. So when it is involved of the two perpendicular line, so you have to divide with 2. When it involves 3 perpendicular line, you have to consider divide with 3 perpendicular line. So what are those, right? 2 perpendicular lines. So let's take a look about this. So for example, the angular velocity, this is just for your basic understanding, yeah. The angular velocity z about the x-axis, about the z-axis is the average. Now we try to look at the velocity, angular velocity in z direction. About the z-axis is the average. Remember the basic definition earlier? The angular velocity is the average velocity of two perpendicular lines. Line segment AB. Where's the line segment AB? From A go to B. And line segment CD. C go to D. The two angular velocity counterclockwise being positive. Right? So, angular velocity A go to B. Where's A go to B? When you want to go A go to B, the velocity vector must V minus A. Remember? Right? In order to get this value, angular velocity A go to B is velocity at B minus A over distance. So how it works? Remember VB, remember we have got the answer. This is the solution. VB is equal to V plus all this term you put inside this equation minus VA. Where is the VA? This is VA. You try to substitute into this equation, divide with dx, the distance. So finally you simplify the mathematical expression here. You will get the partial derivative of v over x. Alright? So this is A go to B. Remember we have two perpendicular line, whereas this is CD. C go to D. Why suddenly it is negative? You must be wonder, right? Why this is negative? Alright? Let me switch on the camera. I hope you can see the reason why it is negative or positive. Alright, so I hope you can see my finger, my hand. So when you take a look about the diagram there, alright, A go to B. So you use your right hand, this is your right hand. A go to B. So your finger pointing upward. A, B. So where's your thumbs? Your thumbs facing upward or downward? Please answer that in your chat. I want to see. This is the direction. A go to B. This is your finger. Okay, A, B. So it pointing this one. And where's your thumbs? Facing upward or downward? Upward, right? Okay, upward is always positive. Remember, we have learned the moment earlier. Upward is positive. However, how about C go to D? C, from the bottom go to the top. C go to D. So where's your thumbs? Facing upward or downward? Please answer the question. I want to see whether you understand or not. Arif, I must say downwards. I believe. Okay. Anyone say upward? It is downward. Remember, downward thumbs is always negative. When it is negative, that's why you can see from C to D is negative. From A to B is positive. This is not mentioned at all, but we know already it is positive. Alright? So that's why it is negative, because the thumb facing downward. Okay, so UD, this is D minus C. That's why D minus C over the distance Y, the change in Y. So finally, you substitute those value here in this equation over dy. You simplify. Finally, you get negative partial derivative of u over partial derivative of y. Okay. Consequently, the angular velocity at z of the fluid particle is, remember, the angular velocity is the average velocity of two perpendicular lines. Where's the two lines? A, B, and C, D. This is A, B, and C, D. So average is 1 over 2. Why 2? Because we have two components, two lines. So substitute back the omega AB, which is partial derivative of V over X, plus, remember this is plus, omega CD, this is minus, plus minus, minus, the partial derivative of u over y. So this is the final equation to get the angular velocity at z component, which is facing upwards or downward. Alright, so I hope you really understand what's the basic definition of angular velocity. So what you need to know, you need to remember the definition, directly translate to the formula. When we talk about the angular velocity, average of two perpendicular line. What is average? Half perpendicular line is plus AB to AB plus CD. So to simplify the equation, we have calculated for every one of you the z component. Remember, this is angular velocity in z component, average velocity, partial derivative of v over x minus u over y, and this is same for y. This is u over v minus w over x. This is for x. On the other hand, is w over y and v over x. This is what, when the question asks, find the angular velocity about the x-axis. That means your thumbs is facing the x-axis. When your thumb is facing the y-axis, make sure your thumb should follow the directions. Alright? So, next, vorticity. Vorticity is somehow related to the angular velocity. Alright? The vorticity is a measure of the rate of rotation of the fluid element as it moves through the flow. Okay? So, in other words, vorticity is the twice the angular velocity. Remember, the omega is the angular velocity. The vorticity is the twice. Multiply with 2. So, when here, we multiply with 2, 1 over 2 multiply with 2, we cancel the first term. So, that's why you will get only the inside term only. Alright? This is what it means by vorticity. So here is the basic formula we have learned, the rectangular. However, we are not learning the cylindrical and spherical. It is the same, where we only need to convert the coordinate. Alright? So far, you only focus on rectangular parts only. Okay. So remember, when the fluid is in motion, alright, there are two components happen. The fluid might rotate and deform. So previously we have learned the rotational of fluid in terms of angular velocity and vorticity. However, how about the deformation? How to explain the terms of deformation? Here we are. We're going to learn about the rate of strain tensor. This is we call it as epsilon. Alright. The rate of strain tensor is the rate at which deformation occur. If AB rotate with the angular velocity different from that of CD, particle will deform. That means will shrink or expand. It will change the shapes. So this is what we call the deformation happen based on the rate of strain tensor. Right? So when we talk about the rate of strain tensor, they're different. Previously, we learned about the angular velocity is the average. Average is the plus. Remember, we plus something and then we divide with 2. However, how about the different? That means different is minus. That's why it is minus here. The difference with AB, angular velocity AB minus angular velocity of CD. This is minus. Previously, you have learned it is plus for the angular velocity. For the rate of strain tensor, it is different. Different from AB to CD. So, this is minus and then we try to substitute the value. Remember, the omega of CD is minus. Minus with minus is plus. Alright? Remember, omega CD we derived earlier. Omega CD is minus. So when you try to substitute in this equation, minus with minus is positive. That's why this is rate of strain tensor in XY direction. Where's the XY? This is XY. The two planar surface, X and Y. This is what happened in the X and Z direction. This is Y and Z direction. Okay, so how about this one? EXX, epsilon in XX direction, epsilon in YY direction. Okay, this is the information. The fluid particle could also deform by stretching or compress in a particular direction. For example, if point B of figure 3.6, this figure, is moving faster than B. For example, B is moving faster than point A. The particle will be, of course, stretching in the X direction. This normal rate of strength is measured by, you can see in the motion occur in the XX direction. This is stretching. B moving faster than A. So it is stretching a little bit. So we can express in terms of epsilon XX, which is B, velocity of B minus velocity of A over distance of X. When the motion involved in the Y, you have to use the partial derivative of Y or partial derivative of Z if the motion in the ZZ direction. So how it looks, the concepts of the rate of strain tensor. Okay. So this is actually the angular velocity where we express the complete tensor as shown below. This is how we present it in terms of metric form in X, Y, and Z direction. This is stress. This is the strain tensor in the XX component, YY component, ZZ component. This is XY, this is XY. This is XZ, this is XZ. This is YZ, this is YZ, and this is YY. So this is how we arrange like this. This is I and J component. This tensor is symmetric, alright? We can see what even it is a change location, it is symmetric. X, Y, Y, Z. Okay. Description of fluid motion. Okay. Now we try to discuss together. Okay. I really hope that you understand on this part. Okay, now we try to do discussion further. So the reason of this discussion to get you familiar with the concept and example, the related problem. For example, we have this question. Okay, please try to read and understand first. Alright, what you have learned here, what you understand from the questions. The velocity field, alright, is given by velocity vector here, 2xi minus ytj, where x and y are in meters and t is in seconds. Find the equations of the streamline passing through 2, -1, which is x and y, and the unit vector normal to the streamline at 2, -1 at time 4 seconds. So from here, how many questions we have? We have to analyze the question. We have two type of question. We have two questions. Find the equation of streamline passing this point and find the unit vector normal to the streamline passing this line at time 4 seconds. So for the solution here, the velocity vector is tangent to the streamline, so that V the cross product of dr equal to 0. Remember, we have learned the velocity in this direction is parallel to the dr direction. When the parallel product having the cross product having the parallel component, so the cross product is 0. So this is the basic definition. V multiplied with or cross product with dr equal to 0. So from this formula, right, we are using this formula in this equation. So where's the V? This is V. Here is V. So V, you try to substitute V is equal the whole component to xi, alright, minus, okay, sorry, okay, for the given velocity vector, we have time equal to 4, alright. So from here, you have to use the time equal to 4. So from here, you try to omit, alright, okay, you try to simplify the equation. This is the time. The time is always fixed for the two questions. Given the time is 4 at the instantaneous time. Remember, the streamline is the measure of the instantaneous flow direction. So at the time of 4, you try to substitute time equal to 4. That's why 2xi minus y t. T, you try to substitute with 4. That's why negative 4yj multiply with I and j. Remember, dr is actually dx plus dy. Okay, let me tell you, I try to make it, I try to draw. y dr is equal to dx plus dy. Okay. Okay, for example, this is flow direction. Okay, this is at time equal to 4. So this is velocity. Okay. Not clear. Okay, this is velocity. Remember, velocity vector is tangent to the streamline. So this is our streamline, tangent to the streamline. So that, okay, this is V. So the R here is, this is R. This is dr. Alright, remember previously we have the reference frame. This is R. Okay. So this is Y and this is Z. This is X component. So dr, in order to get dr, is actually, okay, when you try to zoom in, okay, when you try to zoom, I think you cannot see here. You try to zoom in. Okay. Sorry. Okay. So from here to here, okay, sorry. So this is R. Okay. So from here, okay, the change in here, okay. So actually this one is related to dy, and then this one actually related to dx. So the change in dr, okay, the change in dr, in order to get dr, that is why I component, this is I component, this is y, and this is x. That is why dr here is equal to vector r component here is actually I component and j component. Okay, so I component refer to the change in dx direction. So dx direction and y positive dy direction. So that's why from this equation, okay, they try to substitute in this equation. Okay, so from here, 2x, you try to multiply, okay, I with I. What happened when you multiply with I? You will get the cross product, I with I, you will get 0. So it is nothing. So let's try to work out on this. Okay, I with I, you try to solve 2x dx I. And then you try to solve this one with the other one. 2x multiply with dy. So 2x multiply with dy ij. Okay. And then how to know this is positive or negative? Do you have any clear in mind how to get this is positive or negative? So basically it is the easiest part. I try to show you, yeah. Okay. This is I. This is J, and this is K. Okay. This is K. Okay. So I multiply with J. Can you use your right hand? I open the camera. Okay. I open up the camera. You can use your hand. I go to J. So you can see your thumbs pointing upwards, right? I go to J. Your thumbs, where's your thumb? Upward. So I go to J, your thumbs pointing upwards. So upward is K. Is it positive? Is it K positive or negative? Can you comment there? I want to see you understand or not. When I multiply with J, what's the answer? K positive or K negative? Okay, thank you, Nurul. Okay, and now you understand, yeah? It is positive. Follow your thumbs. It is positive. Okay, so it is I multiply with J. It should be, oh man, okay. So now you understand, yeah? 2x multiply with I dx, 2x dx, I. Okay, 2xi multiply with dyj, I multiply with j is always, okay, you use this, this is I, this is j, this is k. So I multiply with j is positive. So positive 2x dy k. Okay, and then negative 4y multiply with dx. Okay, j multiply with I. J multiply with I. What's the answer? Positive or negative k? Please comment there. Use your thumbs. J multiply with I. Negative. Thank you, Nurul. Thank you, Arif. Okay, so it is negative. Negative 4y multiply with dx. So it is negative 4y dy, sorry, dx. This is k. And then negative 4y plus, this is negative 4y dy j. Remember, when this is the cross product, when the same vector in the same direction, it is 0. Alright? I multiply with I is 0. There is no cross product on I. So from here, you simplify 2x dy k. This is plus 4y dx k. So now you can see, you try to factorize the k. 2x dy plus 4y dx factorize of k. Is it the same? 2x dy plus 4y dx k. And then remember, equal to 0 because v multiply with dr in the same vector direction parallel equal to 0. That's why the whole this term equal to 0. So when this is 0, you transfer this one equal to 0. Finally, you get 2x dy equal to negative 4y dx. From this term, you try to, it will be like this. And then you rearrange dy y equal to negative y dx. Why you need to arrange? because you are going to integrate both sides. This is with respect to y and this is with respect to x. Okay, you integrate this, you will get you try to integrate. Remember, you try to integrate this. You try to simplify 1 over y integration dy equal to negative 2 over x dx. So you integrate 1 over y, definitely you will get ln y. Integration of 1 over y, anything 1 over something, you will get ln. Alright? You integrate 1 over x here, you will get ln x. Remember, this is unlimited. The integral has no limit. When there is no limit, alright, you have to plus constant. This is ln c. Actually, you can put c only, but it is okay. It will be no problem to put ln c because you try to uniform the equation. This equation has ln, this ln. So why not putting the constant to be the ln? So ln c. Okay, where we use ln c for convenience. This is written as ln y equal to ln x. Remember this equation, under the log rule, you can transfer to become the index. So ln x minus 2 plus ln c. So from this equation, when the rule of log, ln plus ln or log plus log, you try to simplify, it will be like this. Okay, you will be ln c x negative 2. So ln with ln, why you try to simplify? Because you want to cancel ln both sides, ln. Finally, you will get y equal to c x the power of 2. You can say 1 over x the power of 2. So you transfer here, you will get x squared y equal to c. So it is the same in this equation. Okay, after you get this term, then you need to find what is c. So from here, okay, you need to find what is c. From the given information, okay, from the given information, it is passing through point 2 and negative 1, which is, this is x and y direction. So this is x and this is y. So try to substitute in this equation. Okay, finally you will get the c is, you try to substitute x squared y equal to c. Finally, you will get c equal to negative 4. So that the streamline pass through point 2 and negative 1. Okay, so this is actually the equation. Okay, now you have solved. Find the equation of streamline. So this is actually your solution. Okay, this is actually your final solution. Okay, the next question. Find the unit vector. Okay. Normal to the streamline. Okay. The first step you have to understand. The unit vector normal to the streamline. We know that the velocity is always tangent to the flow direction. Tangential. So normal. What is normal? So normal, for example, this is the flow. The tangent is like this. The normal is always 90 degree. This is normal. We symbol as normal. And this is tangent. Okay, so now the question asks, find the unit vector normal to the streamline. They ask you to find the n crown. We call it as n crown. Okay. So at normal vector, a normal vector is perpendicular to the streamline, as I mentioned earlier. Hence, the velocity vector using n equal to nx, this is considered in x and y component. Yeah. Remember, when the normal vector, we have I and j component. This is the magnitude in x and y direction. At which point, remember they ask you at 2, -1 at time equal to 4. So, in order, previously, the tangential line, we use the cross product. When it is normal, we use the dot product, alright? So, V is the velocity vector, normal, dot product to the n. This is a normal vector. This is a direction, okay? So, you substitute the formula 4i plus 4j. So, where you get the 4? So, remember, you substitute the x in terms of this. 2 multiplied with 2 is 4. You can see 4. And then y. Y given here is -1. Negative multiply with -1, +1. Multiply with time is 4. That's why you get here is +4. So you try to substitute the value. Okay. Dot product with normal vector x component and y component I and j. Remember, it is in the opposite side. When you use the dot product, alright, due to the normal direction, when it is in the same direction, it is equal to 1. However, when it is in different direction, whatever I dot j or j dot I, it is equal to 0. And this become 4i multiply with I, multiply with nxi, I become 1. So you will get 4nx multiply with 1. And then I multiply with j is 0. You don't have to care at all. You only care I with I, j with j. So 4j multiply with nyj, you will get 4ny. Okay. And then you try to simplify further. Therefore, n of x is equal to -ny. So, then, because n is a unit vector, remember, when it is a unit vector, the magnitude is 1. Nx squared plus ny squared is equal to 1. This is the formula of the circle. Remember how to get the unit vector. I believe you learn from your secondary school to get the unit vector. The unit vector is, this is the formula. Okay. This is the formula to get the unit vector. So, remember the unit vector is always 1 because it is unit. So you transfer here, this is 1, you will get 1 equal to nx squared plus ny squared. That's why you get this term. We find that, okay, ny here, we use this relationship. Okay, and x we substitute with negative ny. Finally, we get nx is equal to 1 over the square root of 2, and on the other hand, ny equal to negative 1 over square root of 2. Therefore, the unit vector you try to substitute here is, okay, Remember, the unit vector is this. Okay, the unit vector is this. Okay, and you got earlier is 1 over square root of 2, and y is 1 over negative square root of 2. You substitute here and then you factorize I and j. Finally, you get this answer. So far, do you clear on how to get the answer, the unit vector and the equations of the vector here? Anyone want to ask any questions? Are you okay? Do you clear about this? Are you okay? Are you there? Huh. Afiq, Arif. Okay, Amirul Hakim 50 there. Okay, that's at the moment. Okay. Amirul Hakim, if you not really familiar, it's okay. My advice after this, watch again my video. Okay, revise many times and work out on the example. Okay. If you don't understand, please ask me. Alright, don't keep silent. It won't help you at all. You have to be active, proactive. Okay, this is the previously you learned about the concept. That's why we give you example to give you understand on the practical part. Okay. I think this one. Okay, I think I will show you in the tutorial. Okay. Now we go on the classification of fluid flow. So, in the classification of fluid flow, previously we learned about the type of fluid description. Next, we learned about class. There are many classification of fluid flow. When we talk about flow, there are many dimensional. We have 1, 2, and 3 dimensional flow. Then, of course, when we talk about 1, it is involved of one space, which is x. When involved of y, involved of 2, which is x and y component. How about the 3? It is x, y, and z component. So the 3-dimensional flow is the velocity vector depend on 3 spatial coordinate. Alright. So here we have x, y, z represent the space and t represent the time. So when we talk about the classification of fluid flow, whether it is 1D, 2D or 3D, to simplify the equation, we have 1 point to another point, point number 1 to point number 2. Alright, then we introduce you the stagnation point. The stagnation point is very important in the engineering field because some measuring meter, for example, the pitot meter or whatever meter, the pressure meter, pressure gauge meter, they use the concept of stagnation point to calculate the value of pressure. So that's why the stagnation point is introduced in this chapter. So what is stagnation point? A point at which the fluid decelerate and come to rest. Suddenly you can see here, this is the fluid motions from the top to the bottom. And suddenly when the fluid encounter the obstacle here, it will suddenly decelerate and rest, the stop. Thus the velocity here is equal to 0. So that is basically the definition of velocity at the stagnation point. Okay. So this is what happened when we talk about 1D flow. The velocity vector depend on one variable, which is when we look at this case, it is depend on the R variable. Why R? Because this is the pipe. You can see this is the cross-sectional of pipe, the one portion of the pipe. So the pipe, we consider only the R component. So this is the R. The R pointing upward. Increasing the R will increase the velocity vector at the middle here. This is normally case when we talk about 1D. In the 1D dimensional flow in pipe. When it is pipe, remember the cross-sectional pipe is circular shape. So when it is circular shape, we use the radius. This is radius. Basically, it's not radius when you look at like this. Okay, for example, this is your eyes. What happened when you look at the cross-sectional? So this is the R here. Or this is the R here. Or this is the R here. Remember the R? This is R. The radius. Pointing upward is X. So this is where actually the velocity reflect only to the R component. So the lower the value of R, you can see the R start at the center. The lower velocity at R, when R is smaller, the velocity higher. When the R is increasing, the velocity is decreasing. So this is where one-dimensional flow. So here is a developed flow. It's one in which the velocity profile does not vary with respect to the space coordinate in the direction of flow. Alright, I think you only learn about this kind of flow. However, when you go into a great detail, there are many kind of developed flow. Fully developed flow, partially developed flow. So I think this is very easy for you to digest. You only learn about developed flow. So when you understand the developed flow, it is one in which the velocity profile does not vary with respect to space coordinate in the direction of flow. So this is the velocity profile. You must be wondering, what is a velocity profile? This one. This is velocity profile. Okay. This we call as the velocity profile. So the profile is actually happen when you connecting this point to this point. So you connect this one, it become a profile, consists of this one. This is all we call as a velocity profile. Okay. So how about the uniform flow, in which the fluid property are constant over the area? So the fluid property, for example, the pressure, temperature, the velocity constant throughout the flow, whatever area. Next, after we have learned about previously, which is 1D, developed flow, uniform flow, and then we go to the viscous and inviscous flow. So dalam bahasa Melayu is kelikatan lah, okay? Viscosity is kelikatan, viscous. Alright, in other words, viscous is the restriction of flow. Alright, it is something that restrict you to the flow. When you into the water, and then you try to swimming, it's difficult to swim. So because of the viscosity, restriction to flow. Have you tried to walk in the water compare walk in the air? Which one is harder? Of course, it is harder in the water because of viscosity. So, in other words, viscosity, it means by restriction of flow. It restricts you from the flow. Okay? So, here, the fluid flow can either be viscous or inviscid flow. Inviscid flow, viscous effect do not significant. There is, but it is not significant. Influence the flow. Viscous, on the other hand, the effect of viscous are important, right? So here, the boundary layer. This is the cross-sectional shape of the aerofoil. So when you look at the dotted line here, this we call as a boundary layer. All right, this dotted line is a boundary layer. Inside the boundary layer, we call as the internal flow. Outside the boundary layer, we call as the external flow. All right, please remember, when the flow is outside the boundary layer, it is inviscid flow. You can see here, inviscid flow. The significance of viscous is very small. However, when the flow is internal flow inside the boundary layer, the viscous effect is significant. Okay? In the viscous effect, the flow will be like this. You can see this is the velocity profile. The velocity profile, this is the surface of aerofoil. And then the velocity at the near wall is 0. Up to the wall, away from the wall, the velocity try to develop, increasing and further increasing. This is the effect of viscosity. Alright, there's the restriction of flow from the aerofoil surface. Okay, you can see this is the inviscid flow outside. This is outside. Remember, outside of boundary layer is we call as a free stream. This is a free stream. Alright, next is the classification of fluid flow, laminar and turbulent. Okay, laminar. Normally, when we talk about laminar, it is in a slow speed. When talk about turbulent, it is very fast speed. The laminar is where the flow with no significant mixing in particle. Alright, but with significant viscous shear stress. Okay, in other words, to simplify this term, I try to share you the example. Right, the laminar is where the flow is the structure, always the straight line flow. The turbulent is the chaotic flow. The flow very irregular, so that the flow quantity random variation. Okay, I try to show you one example. Different between laminar and turbulent flow. Okay, analogy. Okay, which one, yeah? Okay, I think this one. Can you see? Alright, this is the smoke. Okay, this is the smoke at the inlets. The starting, the smoke will flow like this. After sometimes, the smoke will be like a chaotic, disorderly manner. So this is because of the turbulent flow. And this is lamina. Lamina is like the flow is very smooth or in orderly manner. The turbulent, the flow is become like this, chaotic flow. It is fluctuating flow. It is not follow the rule. Okay, that's why you can see the laminar flow, the particle will not mix. It will flow steadily, steady flow. However, for the flow of turbulent, the flow very irregularly. So this is A, you can see this is fluctuating. So what is this? This is turbulent flow. When the flow consider no variation with time, the velocity no variations. Sorry, yeah. Okay. Alright. So when the flow is no change in, there's no variation of velocity over time, this B we call as the laminar flow. You can see this is the steady flow. This is unsteady flow. So in the normal case, in the real situation, the velocity is fluctuating over time. Alright? And mathematical expert has tried to simplify the fluctuation flow. They try to convert this one to become the average flow. Later on, you will learn about the Rand's turbulent model, which we call as Renault average Navier-Stokes turbulent model. This is later on, but the most concern here is you need to differentiate or distinguish what is laminar and turbulent. When someone asks you what is laminar, what is turbulent, laminar is the flow is steady flow. It is not fluctuating. It is orderly manner. However, the turbulent is the flow is irregular manner, fluctuating over time. Okay, so how do you quantify or distinguish whether the flow is laminar or turbulent? So there is one professor we call as Osborne Renault, all right, that proposed the theory of Renault number that can predict the flow regime. So they propose the formula is velocity time length. Length is a characteristic length over kinematic viscosity. All right. Sometimes when the flow velocity is high, more than the critical Renault number, we consider as the turbulent. When the Renault number you calculate less than the critical Renault number, it is laminar. Okay. So you can see the Renault number is a function of velocity, length over viscosity. The higher velocity, the higher Renault number, and vice versa. Lower velocity, lower Renault number. So you can actually see that higher velocity will tend to direct you to the turbulent flow. The lower velocity will give you the laminar flow. Okay. So normally this is we call the critical Renault number. This is your point reference. If the flow around the rough wall pipe, the Renault number is 2000. Alright. When the Renault number you calculated more than this number, it is turbulent. When the Renault number lower than this, it is laminar. This same goes to parallel pipe and flow on the flat plate. This is the critical Renault number that you have to understand and remember. So this is, you can see the boundary layer flow on the flat plates. So you can see the laminar is the straight flow, and suddenly there is the transition from the laminar to the turbulent. This is completely turbulent. So they will encounter the laminar flow. Alright, this is the our universal phenomena happen in the boundary layer flow. Okay, this is example. Okay, I think I will show you later on. Classification of fluid flow. Previously, we learned about the turbulent and laminar. Now we go on the incompressible and compressible flow. So it's very easy. In the fluid, there are two components: compressed or cannot be compressed. So when it is cannot be compressed, you try to push this piston, it will not move at all. When it is compressed, it can move. For example, incompressible is like a water. You try to compress the water, it is harder. So the density is constant. When you try to push the air or any gases, it will be easier. So that means it is compressible. So the density will vary because density is the function of mass over volume. The change of volume will change the density. Okay. So next, we learn about the Mach number. So this is the Mach number. Actually, the Mach number is related to the flow velocity with respect to the speed of sounds. Right? For example, there is the rocket or jet moving at 3 Mach number. So it is 3 times the speed of light, the speed of sound, sorry. So the Mach number is the gas flow parameter. That is the ratio flow velocity to that the speed of sound. So the formula is the velocity of the gas, the flow gas over the speed of sounds. So we know that the speed of sound is square root of kRT. K is the specific is the K is Cp over Cv. Alright, the ratio of specific heat ratio. R is a gas constant and T is temperature. All this in the absolute number. If Mach number is less than 0.3, the flow is assumed to be incompressible. Alright? So that means if you have the indicator that the question asks, the Mach number 0.3, so that means the speed is very small. For example, you reduce the Mach number, the velocity is very small. So when the velocity is very small, definitely it is involved of water. The water moving the velocity very small compared with the air. So when you move, for example, when you try to move, okay, for example, when the Mach number is less than 0.3, alright, this is the speed reflect to the velocity is very, very small. For example, this is water. You try to move and suddenly you realize that your velocity is very small. So the smaller of your velocity reflect to the lower Mach number. For example, if the Mach number is more than or equal to 0.3, that means it is involved of air. So your speed is very faster. So velocity is higher. So when it is in the air, definitely it can be compressed. This is water. So incompressed. That's why the flow is assumed to be incompressible if the Mach number less than 0.3. That means it is involved of water. Okay, it is incompressible. Next, we go to the last chapter, which is about the Bernoulli Equation. So, this is actually the derivation of Bernoulli Equation. Okay, the Bernoulli Equation states that for an inviscid fluids flow, an increase in fluid velocity causes a decrease in pressure or decrease in potential energy of the fluid. So state that. So the Bernoulli equation is actually assume that the flow is inviscid. There is no viscosity is insignificant. So the viscosity refer to the no shear stress. Okay. And the steady flow. Okay. I think I want to explain a little bit about the shear stress. Okay. For example, this is the fluid. The fluid is go layer by layer, yeah. Okay, this is layer 1, this is layer 2, layer 3. Okay, this is the surface. Okay, because of surface, it try to restrict, this is the flow. It try to restrict back the flow. So the flow at layer number 1 is harder, is more harder, difficult to flow because of reaching to the surface. Okay, because of the friction. So layer number 2, what happened? This is slower. It try to influence layer number 2. Okay, I give you this is maybe the friction maybe in term of 10. Okay, I give you 5. A bit. Okay, and then the next layer will try to influence another layer. I give you maybe 3. And smaller. So you can see this kind of property we call as the shear stress. All right, they try to move, but there is the shear. The shear is always parallel to the motion. So because of this shear stress, the flow will become slower and slower. Okay, that is what we call as the no shear stress. If there is no shear stress, that means the flow has no shear. You can see the arrow here. This is the shear. When no shear, that means there is no arrow at all. The flow smooth. Alright, so that's why assumption of Bernoulli is no shear stress. The flow is steady, no change of property over time. Along the streamline, constant density, that means it is incompressible, more on water, and inertial reference frames. Okay, so based on this equation, based on this the flow, this is the fluid particle, right? This is a flow field. The flow in this direction, tangential to the flow field. This is velocity vector, and then this is dA, ds, the change in the distance. All right, this is radius of curvature, and this is dh, and finally they do the mathematical derivation. It come out with this equation we call as the Bernoulli equation. So Bernoulli equation come from this expression, infinitesimal derivative. Okay. V is a velocity over 2 plus pressure over density plus GH equal to constant. So between 2 points on the same streamline, we can say that this is constant. We can equate it as equal. Velocity 1 equal to velocity 2. Then come into this equation. Velocity 1, velocity 2. So we try to change 1, 2, 2, 2. This is between 2 points. And another form of Bernoulli equation is we divide with gravity. So from this one, all this one we divide with gravity. We got here 2g rho g and h only. You can see this is g, rho g is, we convert to gamma and become this equation. Okay, so sometimes when the question asks between 2 points, point number 2 reflect to the stagnation point. That is why it's very important you understand the stagnation point, where you consider the velocity 1 given and velocity 2 is 0. Remember, the stagnation point is where the flow come into rest, decelerate and come into rest. So this is actually the measuring device. Measuring device number 1, you can see here on the left side is the piezometer. It's used to measure the static pressure. The middle part is pitot probe. It's used to measure the total pressure based on the stagnation point. You can see velocity at 1 go to velocity 2, it try to decelerate because this is the obstacle. When the velocity decelerates and it stop at 2, we can use the Bernoulli equation. You can see velocity at 2 cancel, it becomes 0. Finally, you will get the answer here, the total pressure P2. So all this based on the Bernoulli equation. So however, there is another device we call a pitot static probe. The right side is a measure the difference between the total and static pressure. So this one, pressure P2 minus P1, we got here using this device, pitot static probe. Okay, so normally the Bernoulli equation is very useful when we encounter this kind of problem, where this is the ball, we have point A, B and C, and this is the flow separation. It separates the stream flow with the wake. We call this as the wake region. Okay, this is the thin boundary layer. The maximum pressure at stagnation point A and C here is velocity is 0 because this is the stagnation point. When the velocity encounter A perpendicular, it will stop immediately. That's why we call it as the stagnation point. Alright. However, for C, it is the wake region. This is the flow is reverse flow. That's why the velocity is 0. Normally, the velocity at B is maximum. So this is the equation. Show that the pressure change normal to the streamline. For example, this is, let me explain a little bit about this equation. Actually, mathematical has derived this equation when the flow like this, okay, this is normal. So the point number 1, the pressure point 1 and point 2, pressure at 3, you can calculate directly based on this formula. So they propose the equation as the equation above showed how the pressure change normal to the streamline. This is normal, pressure change, pressure at 1 will be different from pressure at 2. So you can see that the change in pressure is negative. Alright, negative means decreasing. So the incremental pressure change short distance, the pressure decrease in the n direction. The more the pressure, the more the length here, the pressure will decrease based on this relationship. So this is how they use the equation to solve this. Later on, I will show you example. Okay. So in summary, previously we learned about Eulerian. Remember that Eulerian involved of the space and time. You can see here, acceleration we derive from the derivative of velocity over respect to time. This is the Eulerian description. This is space, x, y, z, and time. And this is the angular velocity with respect to the average perpendicular to line. This is line A, B, and C, D. And the deformation, we focus on the rate of strain tensor, epsilon xx. This is stretching, this is compression, all right? We have learned previously. And the fluid flow can be either steady or unsteady, viscous or inviscous, laminar or turbulent, compressed or incompressible. And last but not least, this is the Bernoulli equation. I think this is very important for you to remember. Velocity over 2, this is the kinetic energy. Kinetic energy, which is half mv squared, right? This is the potential energy. This is pressure energy. We combine all these, we got the total heat, total energy. Okay? This is between 2 points. And then last but not least is the pressure change normal to the streamline. I think that's all about this chapter. Okay, I hope that after this, please revise back this lecture. I send you this video. You try to focus more on what you are not understand. For example, you have not understand subchapter on Bernoulli. You go to the videos sections specifically focus on my lecture on the Bernoulli equation. So, and then you will understand more easily. After this, I will post this video, yeah? And the next tutorial, we will try to do example together. So we will be understand much more easy to do for to help you for the exam. Okay, so I hope that you understand clearly. If you are not, please, I wish you, I hope that you revise back this lecture. Okay, it's very important for your understanding the concept. Okay, so for those who still not scan the QR code, please do so. Okay, in order to record your attendance. So far, do you guys want to ask any questions? Are you there, everyone? Okay. Okay. Thank you very much. Thank you, everyone. I hope that I give you assignment. Your assignment is to revise this video. It's very important to understand. Okay. And for those who still not scan the QR code, please do so. Okay. Okay. So next time I will use this QR code for the next class. All right. So I think that's all for today's lecture. Thank you for your time listening to my lecture, and I hope that you revise after this. Okay, before 24 hours. All right. Okay. I think that's all. Thank you, everyone. Assalamualaikum warahmatullahi wabarakatuh. Okay, bye.
Thank you, Doctor. Waalaikumsalam warahmatullahi.
Waalaikumsalam, Doctor. Thank you.
Okay, I will share the video after this. Okay, bye.